Okay, so let me introduce Professor Robert Fergus from Facebook AI Research and New York University. He will be giving us the talk about the MazeBase project. So we hope that this will inspire the whole participants to win the hackathon task and to make research in the field more thoroughly. So thank you, and let's welcome our guest.
Okay, well, thank you very much for inviting me. So actually, I'm very excited to come to Russia because, in fact, my brother has spoken a lot about it because he actually teaches Russian. He's a Russian language lecturer in the UK, so he actually, does Russian literature and Russian language. So anyway, he's visited many times, and so this is my first time to the country, so I'm very pleased to be here. Okay, so unfortunately, he inherited the gene for speaking foreign languages. I just got the one from math and science, so I'm going to speak in English. No, Russian, like my brother. Okay, so this is a project that we've done at NYU and Facebook. So actually, the main person behind it is actually my PhD student, Sam Bayar. So he's the picture of him. Okay, so what is this thing about? So it's effectively a simple environment for AI-related games, where we have, as we'll see, it's a really very, you've probably seen things like it before, but I think, as I'll explain, it is actually quite different, perhaps, to many of the sort of things out there at the moment. And we're going to use it for exploring a variety of games that are essentially embody some very simple abstract reasoning. Okay, so this is a sort of topic which has been sort of quite popular recently. And with Jason Weston, I perhaps talked about these Babi tasks that you've heard about. And you can think about these as a sort of spatial form, if you like, of these Babi tasks. And effectively, we're going to use reinforcement learning in this little sort of game world setting to explore abstract reasoning, and I'll explain sort of how that works. Okay, and this talk really is it's not particularly technical, so it's quite late in the day. Hopefully, so it's not going to be too taxing for you. This is essentially more of a kind of it's sort of different perspective perhaps on how to think about developing new models and things like that. So the models I'm going to show none of them are particularly novel. You've seen them all before. But this gives us a nice sort of way of evaluating them and perhaps indicating directions for future research. Okay, so let's just talk about MazeBase itself for a second. So I guess the motivation is we want an environment which is going to help us develop new algorithms. Okay, so there's obviously lots of problems we're interested in. It's quite hard coming up with new models, and we want a sort of nice, very simple environment in which we can test them out and perhaps tweak them and find better ones. Now, of course, quite a few people have thought about applying, in particular, deep models to playing games recently. So there's a whole bunch of work that you're probably familiar with in that space. And I guess most of the focus on the development we're interested in is also about deep learning, models for deep learning. But one drawback to the sort of current games that people use with these deep learning models is that they're sort of fixed games. Okay, they're sort of predefined. You can't alter them. It's not quite clear how you would if you wanted to make the game harder or something like that, how you would do so. And so you can think about this as a sort of sandbox, a sort of an environment for playing around to develop new models in. Okay, now I think this work is inspired to some extent by some of the work that Tomasz Mikolov, who I guess spoke, was it yesterday, about his roadmap for how we should go about solving AI. And one of the things he had in there was this notion of somehow a little sort of toy environment where you had, which was simulated, and you would essentially ask questions to some little agent, and he would do things and then ask, tell you things back. And you can think about this MazeBase project as a very sort of simple first practical step trying to instantiate that. Okay, so obviously there are many aspects to what Tomasz was talking about that go a lot further than what I'm going to explain, but I think this is a very basic first attempt. Okay, so the environment itself is actually incredibly simple. It's not, you've probably played around with things like this before. The idea is you're going to have a small little 2D grid, a series of discrete locations, and you have a little agent, this little red blob that's going to go around and do things, okay? And you'll have different objects in this world, things like walls, which you can't pass through, things like water, which you might incur some penalty for crossing, and then you might have various goal-related objects, which I'll explain more how we use them in a moment. And one key property is that it's easy to kind of randomly generate these kinds of environments, okay? You can have essentially we can generate many different environments that basically encode similar types of problem. And this is, of course, different if you think about it, your standard video game where typically the levels are predefined. In this one, we can sort of generate as many levels as we want, and we'll be able to vary the difficulty of them also programmatically too. Now, within this environment, we're going to have a whole range of different tasks. And the idea is to sort of reuse the same kind of elements for different tasks. So we'll still have blocks and water, but we might change what it is that the agent's supposed to do. And we're going to specify a bunch of objectives for the agent in terms of text. Okay, so the text might be, it describes essentially the task. So, for example, the task might be to visit goal 4, then goal 2. Okay, and then the agent would have to, the whole task essentially is to try and learn what this means, and then the agent would hopefully be able to go and execute that kind of thing. Okay, so just to give a bit more detail, we have a bunch of static items, as I said, things like blocks and water. We have a bunch of interactive items like blocks. You can see this little agent here pushing a block. We also have switches, which in some of the games we use, which will perhaps determine whether you can pass through a door or not, just like in a super simple adventure game. And then we have these information items, which, for example, don't really exist on the actual little 2D world, but they contain, they're a way that we embody the instructions that we're going to give. For example, the little, this thing we saw here would be an instruction item in the environment. Okay, so and just to understand how these things are encoded, so basically we're going to use text. Okay, so very, very simple language. Even though, of course, we're rendering this into sort of pixels, we're not going to use the pixels themselves. It's just going to be a text-based environment. And the agent just gets to see basically a list of sentences, and each sentence is going to sort of encode one of these items. So, for example, you might have the sentence might say something like, there's a closed door at a certain location. Now, everything is going to be represented by a word. So, for example, there has, in the model, we'll have, this is one particular model, but it's easiest to explain it with this one. So here we go. For example, a location is just going to be a single word. So, this in the case x1, y3, that's just going to be one word. And we're going to arrange the locations anyway in the sort of egocentric coordinate frame. So what that means is everything is relative to the agent. Okay, so you can see here that there's a block here, which is y minus 3x0. So you can see the agents here. So you go 3 up, 1, 2, 3, and there's a block. And then we'll have a separate word for being block, and this will be the sentence that describes effectively this object in the maze. And we have a whole bunch of these things here like that. And then, as I mentioned, we have the objects in the world, but we also have these sort of information items, which I'll talk about. Which now the most obvious of these is the task description. So this is one encoding a little problem, which says if the color of the switch here is color 1, then you should go to goal 3. Otherwise, you should. If the switch is a different color, then you should go to goal 2. So this is encoding a little sort of conditional reasoning problem for the agent that it has to do. So it has to know to sort of go and look at what color that switch is, so it can see that. So it's able to see in its environment the color of the switch. It doesn't actually have to physically move over there. And then based on the fact it's a color 2, its objective should be to goal 2. Okay, and that would be the way it would solve this particular problem. But you can see it's a very general framework. It's designed to be sort of quite compact, and we can encode a whole bunch of different problems in this way. Now, one thing to mention, of course, is that the way we're encoding location here is, it's one way of doing it. Obviously, it doesn't really respect the fact that you're on a sort of 2D grid. So the algorithm's going to have to learn by itself that, x1, y3 is next door to x1, y2, for example. Okay, that's not something that's inherently given with this particular representation. Of course, if we use the pixels directly, we will get that kind of thing for free. But so that's one slight drawback we have at the moment. But it is very flexible. Now, okay, so that's a sort of high-level view of. That's really, in fact, all the detail there is about the environment itself. I just want to spend a little bit of time motivating why this isn't just something you've seen before, and why perhaps it's an interesting problem or interesting space in which to explore a bunch of machine learning algorithms. Okay, so there's a whole actually little community out there of people who study video games for AI. Okay, they're actually not so much in the machine learning community. They actually in the sort of AAAI and InchKai and venues like that. So Google DeepMind, for example, they actually had a whole bunch of, sponsored one of these things. There's a whole bunch of, these, again, 2D little platform games that people had built that they managed to sort of package and use. And then there was also playing Super Mario. So the idea is you have to get Mario to run along and pick up the coins and rescue the princess and things like that, all under the control of some agent. Okay, so that's the two of them. There's another one, perhaps, which most of you are probably familiar with. I know some of the, Evgeny, for example, is very familiar with this arcade learning environments. This was a bunch of old Atari games where you had Space Invaders and things like that. And these, I guess, have been very popular recently as an environment for trying out reinforcement learning with deep learning. And people have had a lot of success with that. Okay, so what I'm going to do is just sort of highlight how I think this MazeBase thing we're trying to do is actually really quite orthogonal to these types of environment. Okay, so first of all, I think the very high level, there's this sort of fundamental issue of planning versus learning. Okay, so most of these environments that I just mentioned, they have some sort of simulation ability. In other words, you're able to sort of say, well, okay, if I move to the left, then my game environment would be in this state, and then I could move up, and then it would be in another state, and so on. And I can search, effectively do a big sort of tree search of all the possible moves that I would like to make, and then try and find outcomes that would give high reward or win the game or something like that. And therefore, in some sense, the algorithms that beat these games, like Super Mario, end up being some kind of search algorithm. Okay, the fact that you have this simulator available to you means that you sort of default to that. Now, in MazeBase, we deliberately decided not to have any kind of simulator available. So in other words, you're not able to kind of just sit there and just, in your current location, run all kinds of possible scenarios and then find one that, gets you to solve the problem with the cheapest, in the cheapest way. You have to actually learn about the environment and understand, well, the water's bad for me, so, I don't want to go there, and so on. Now, I have to say, this is the way it's currently set up. I think at some point we would want to have some kind of planning, but the point is we don't want to expose to the model any direct simulator. I mean, you might be able to learn a simulator, but at the moment, but we're not going to give you one for free, for example. Okay, so now learning about this environment, you might say, well, that's kind of weird. If the agent's just playing these games, how does it know what the rules of the game are? I mean, how does it know what, that a block is bad, or so the water's bad, or I can push a block and things like that? Well, the key to that is actually to have essentially this joint training idea that we've got a whole bunch of games which reuse the same objects in the world in different ways, and we're going to train simultaneously on all of them. Okay, so in that way you can discover, well, I actually do get bad reward when I spend a lot of time walking through the water. So effectively, we're going to be using reinforcement learning in this whole within this environment. You're going to be able to sort of figure out what it is that each of these different objects does in the world, and that's sort of fundamentally different to a lot of these other tasks where people tend to train sort of individual in each game. You don't see this sort of training simultaneously on all games at once. And then also in some of these environments, they actually do give you the rules as well. So you're able to sort of, check all the different things you would like to, all the different actions you could take. You can check whether they obey the rules or not like that, or perhaps encode the rules into some sort of tree search type thing. Okay, so another thing which I think is also very important from the point of view of sort of developing new algorithms and particularly training them is that we're able to programmatically control everything. So we can control the size of the maze, we can control the number of blocks, the number of goals, essentially the difficulty. And this is crucial because if you're trying to, if any of you played around with things like reinforcement learning or these things, it's very difficult to start off with a very super hard problem, right? The model starts off a random kind of initial policy, it sort of fumbles around and doesn't really discover anything. If you have a curriculum, if you can start out with very simple problems, where by chance it will sort of discover how to solve it, in a fairly short time, and then by that mechanism sort of get some clue about what it's supposed to be doing, you can then sort of ramp up the difficulty, and in that way actually get the thing to solve quite difficult problems in this sort of incremental fashion. And the difficulty is if you've got a sort of rigid game environment, something like Atari, where the level difficulty is kind of pre-specified, you can't do that. Whereas with us, we can sort of, it's all under our control, so we can see if the learning algorithm is struggling. Maybe we should give it some easier training examples, and hopefully it might then pick up something. So that is actually, as we'll see, actually very important to be able to get even quite simple algorithms to work well. It's giving it some kind of curriculum. And the other thing I guess I already sort of discussed at some level is that we're going to use a sort of text-based representation. I mean, you know, you could argue, yes, well, there'd be ways to sort of do things with pixels. I think one of the things we do want to do, of course, is to be able to have a representation that transfers to new domains fairly easily. And at the end, I'll show you how this actually can be pretty powerful, how we're able to train on, you know, in MazeBase and then test in a completely different environment. And the models still generalize effectively. And if you have pixels, you know, it can be maybe perhaps a little harder to do that. But also, you essentially bypass this whole perception problem. I mean, now that ConvNets work so well for image recognition, maybe it's not such an issue, but you know, so it's one thing that makes things a little easier. Now, the other thing is that most of what I'm going to talk about today is actually the sort of simple algorithmic reasoning problems. And that's a bit different to most of the, so most of the games, of course, are focused on, I don't know, making people happy or something like that, right? There wasn't a kind of explicit motivation behind the game design. So the games we're going to design, of course, aren't really designed for sort of humans to play and find them fun. They're designed to actually try and explore our ability to get these deep models to do kind of simple reasoning. And that's, you know, obviously a very hot area at the moment in machine learning. You know, all this work that various people, DeepMind and Facebook and other people are interested in is all about, you know, this kind of abstract reasoning. And many of them are exploring that in a sort of very abstract setting, you know, looking at sort of abstract algorithms, can you add two numbers and things like that. And the catch is, of course, that this kind of lacks any grounding. You're not tying it to anything sort of real objects or anything like that. And much of human reasoning does have some grounding. So maybe there's, maybe this, you know, this, I guess, is somewhat a different approach to exploring this kind of whole idea of reasoning within machine learning. Okay, so that's, I guess, the sort of overview of why it's perhaps different, this whole MazeBase environment, what we're trying to do with it. Okay, so if anyone has any questions at this point, maybe we can, I'm happy to take them. Of course, at the end, you can talk to me as much as you wish. Sure, Mikhail. Yeah.
Does the agent have all the knowledge about surrounding environment or just part of it?
So right, that's a great question. So at the moment, it does actually get all the environment. That's right. So it can effectively see the whole maze from where it's standing. You could imagine, I mean, we're thinking about scenarios where, I can tell you about them at the end, where we know where the agent can only see a sort of its neighborhood, and then it has to walk around and remember things it saw previously. But at the moment, we're going to sort of make life easy for it. And yeah, it gets the whole thing. So it sees everything is the point, yeah.
Does the agent see the image or some description?
No, it doesn't see the image. It doesn't see an image. It just sees this on the right side. It just sees a bunch of sentences describing the thing.
So
yep.
to understand you correctly, if,
Yep.
For example, the agent moves,
Yeah.
so all the coordinates in the description.
Yeah, exactly. That's exactly right. Sorry, I should have said that. That's right. Because it's egocentric. That's right. If this guy moved one step to the left, all the x coordinates here would change, because in some sense, all, you know, the objects are staying still, and the agent is moving. Yeah. Yeah. Sure. Yep.
Can you please explain one more time what does the lack of the simulation mean?
So, right. So if let's take something that people are familiar with, perhaps like playing chess, or I don't know if you've been reading the articles recently, playing Go. So when you're in a particular board configuration, you're able to fairly cheaply decide, you know, figure out what the board environment would be at the next state, right? So if I move my queen, you know, one square forward, then I have a new state, and then you can imagine, you can essentially keep exploring a whole bunch of moves, and then eventually at the end of the game, you would have some outcome, you win or you lose. So you end up with this big tree search to try and find moves from the current position that would end up, you know, with a high probability of winning or something like that. But to do that, you have to have some way of knowing that if I move my queen one step forward, what the new configuration of the board would be. Okay, now in a board game or something like that, it's easy. Of course, in real life, it's very complicated, right? If I push this, I have to have a good model of, you know, well, the thing's heavy and it'll fall on the floor and break into pieces and stuff like this, right? So, and if you have an agent that wants to do smart things, normally, you know, you want to have it to have some kind of ability to plan different actions. And certainly in these types of games, they give the game engine is available to your agent if it's trying to plan the next move. In other words, it's able to say, well, if I, decide to shoot my gun, this is what would happen. Okay. Whereas in R1, we're not going to, at least in the current things I'm describing anyway, we're not going to allow the model to kind of run the game engine many, many times, which is what you would need to do if you want to do the tree search type things from your current state, right? So it has to basically just look at the current state, run it through some, neural network type model, and that will then predict what it should do. Okay, you're not allowed to sort of try a whole bunch of things, and then see what the outcome would be, and then make your selection based on that. So hopefully that's clear. Yeah.
So is there any further plans to maybe make this environment possible to handle several agents?
Yes, I'm going to talk about this at the end. Yeah. Okay. Yeah.
Well, in real life, the cognition, we try to simulate these models. We don't explicitly build the tree and
that's right. That's right.
Heuristics, but I was wondering if there is a way to track if this neural network has managed to itself learn this simulation, or even the depth of the tree.
Yeah. So that's a great point. So actually, at the moment, I think this is what we're looking at into next. So that's a great question. So to bridge the two worlds, right? So obviously it's clear that we do some kind of planning, right? But we don't use tree search, but we have some sort of internal model of like what will happen if I push the speaker off the desk and stuff like that. And it's clear that we learn that ourselves, and that's really what we're thinking about next, actually. So I'm not going to talk about it in this particular talk, but we're thinking about how the ways for the model to learn, what will the outcome of various things, and so on. So we don't directly probe whether it's doing that already at the moment. I mean, it might be doing something, but I think it's a super interesting idea. There's a few interesting papers coming out actually about this. Like Hong-Nak Lee's group at NIPS this year had a fun one, like trying to learn a predictive model for those Atari games, for example, so that it would just look at the configuration and it would predict what would happen for the next few moves and things like that. So it's something that people are thinking about. But the key difference is you're sort of, the predictions being made feed forward rather than actually having access to a sort of an explicit model of the world. You're kind of have an internal model of the world, which is you're going to use to sort of predict what will happen. Yeah. Okay. All right. So let's talk about the tasks themselves. So the current set that we're going to play with is actually 10 different things, which embody some different types of reasoning. And as I mentioned, because we have programmatic control over everything, we can easily vary the difficulty of each of these tasks. And the only thing that's really going to change in some sense is the different info items we give that define the tasks, right? So the 10 different tasks will have different info items, and we can randomize within a given task. So for example, one of the games is going to be to sort of go to all goals except a certain set. So we could, this could, for different instantiations of the game, could be, go to all goals except goal 3 or goal 2 and 4 or something like that. And of course, the layout of the board is going to be randomized as well and that kind of thing. Now, the only supervision we're going to give to the algorithms is some kind of reward when the task is completed successfully. Okay, so and we do, to try and encourage the thing to sort of hurry up and get on with things, we do give it a small negative reward for each step. So if it's just fumbling around trying some random strategy, it may well end up solving the task, but that's not a very good policy. We'd like it to learn something smarter, and one way to encourage that is to just give some small negative reward. We also, if it touches water, it also gets a negative reward as well. That's one way to sort of get it to sort of trying to learn to navigate around water and things. Okay, so now what are we going to try and explore? So in this simple environment, we can actually encode some fairly, they're not complicated, but some sort of basic reasoning principles. So one thing would be sort of operations involving sets, like you've got to iterate over a list of objects like goals you have to visit. You could say, I want to visit all goals except those I specify in some other list. You can do sort of conditional reasoning. So you saw that a little bit before, like, if the color is, color 2, then you should go to goal 3. If not, you should go to goal 5 or something. So that's a kind of if-then statement. There's also ways to do while statements and things like that. You can do basic arithmetic, as I'll show. One of the games embodies that. And some of them involve manipulation of the environment. You're going to have to push a block, or you're going to have to toggle a switch and things like that. Okay, so I'm just going to quickly go through the different tasks, and you can get a sort of flavor as to how the sort of, these are just things that we came up with that would instantiate these different concepts, and we can see whether the existing models we have are able to kind of, solve tasks that involve these kinds of reasoning concepts. Okay, so hopefully this is the video part. It's always a bit precarious in any talk. So let me, okay, so sorry, there's me speaking in the background, but maybe I'll just turn down the volume. Okay, so this one is a very simple one. This one, the information would specify a certain goals in a certain order, and it has to just then, read basically that. So I don't know, maybe sorry, the video clip's very short, but the idea is basically it's got to wander around and visit, certain goals in a certain order. This one is so related to it. There's a game we call exclusion. So this one's you just got to visit all the goals except those in a certain list. Sorry, I should have shown here the information item that goes with each of these different games. Each time it sort of changes over to something new, that's a different instantiation of the same task, and you would have a different information item, which I guess I didn't put up here. Conditional goals. So this one does conditional reasoning. So this one, for example, it has to look at the color of a switch and decide based on that what it should do. So maybe the, in this case, the information item says if the switch is gray, the goal is G5. So hopefully it will, these are showing little examples of models that have already trained, of course. Initially, it's just bumbling around. So it's supposed to go to G5, and then it will, it's won the game or whatever.
So these instructions and goals are not changed during each step?
No, it's each different instantiation of the game will have a different goal, for example. So, a different version of this conditional goals game might say, if the switch is, red, go to goal 4. Or something.
So when it moves to one cell, the instructions do not change. So
within one game, the instructions stay the same. But when we...
And the reward is only
at the end, that's right. So we don't give it a supervision saying, okay, now you should go left, now you should go right, and then you will achieve the goal. Okay, so this is another one where we have to take up all the switches and they have to be toggled. So when the agent moves over a switch, the switch changes color. And what we have to do here is try and toggle all the switches to be the same color. So that's one that requires it to sort of, yeah, this one's a bit weird. I think this is the first couple. I'm not sure what's going on in the first couple. These ones are already both cyan. This one here, it has to make them all yellow, I think. What's happened? Yeah, there you go. So it has to make them, you can see it's going to run over and then it's 1 because it made them all change to yellow. That kind of thing. There's another one which there's a door, and because it's all random, sometimes the goal is behind the door. In this case, it's actually on the same side as the door. But if the goal is behind the door and then it's initially locked so that the agent can't go through, and what it has to do to unlock the door, it has to run over, toggle the switch, and then it will be able to go through the door. So this is like a super simple little adventure game. And the thing does, so it requires you to sort of manipulate things and kind of do some reasoning, saying, well, is the door open or not, and stuff like that. So in this case, the goal is actually on the same side. So not particularly interesting. So this one, oh, sorry. I just picked these examples randomly. Most of these aren't. This one is unsolvable. Okay, here we go. So it has to run over to the switch. The door now opens. That's why it's green on that side. And then it can run over and find the goal, that kind of thing. Then we also have ones where it has to do some basic arithmetic. So we can give a target location for the agent. It has to go to a certain position on the board. Now, if you remember, we have this object-centric agent-centric coordinate system. So it has to be able to know how big, so if you say go to 3, 3 in absolute coordinates, it has to map between these relative and absolute coordinates. To do that, it needs to know the size of the board, and we give it some sort of corner objects, which are invisible, that basically tell it the dimensions of the board, and then it has to work out for itself, where is it relative to that thing. So it's not exactly arithmetic, but it has to do some sort of numerical comparison. And then there's another one, which is very related to that, where you don't give it directly the location, but it has to look it up in an indirect way within the instructions. We also have one which I guess I showed earlier. This is one where the agent has to kind of push a movable block to a certain spatial location, i.e. one of the switches, and then it completes the game. And then we have a simpler version of that where it just has to simply push the block to one of the edges of the board. So it has to know where it is and so on. And you can, so in this case, it just had to push it onto the right side. In this one, it's got to say push, I don't know which way it's got to push it. or I guess the top edge, or something like that. And this one is, again, sort of a little adventure game type thing. So there's a block that's usually in the way to the goals. In this case, actually, the goal's on the same side as the agent. But, okay, so that one's not very interesting either. Okay, so sooner or later we'll have one that's interesting. There you go. Okay, so now it has to push the block, and then it can get through to the goal. All right, now what we're going to do is we're going to try out these different games. Yeah, sure.
Why is it different times between frames?
A different.
If you notice that frames are different, delayed frames.
Oh, I think that's maybe just the fact that PowerPoint's kind of slow. Yeah, I mean, there's no notion of. I mean, the time is discrete in this world, right? It takes, it makes a move, and then the game state updates and things like that. There's no. It's not continuous. There's no. Although we can handle that. So I'm going to show an example at the end where there is a sort of more continuous notion of time. Okay, now what we're going to do is we're actually not going to really introduce any particularly new models here. The idea is to just try out a lot of the deep models that all of you are probably familiar with on these different games and see how they get on. Okay, so we all sort of ConvNets have worked really well for lots of tasks. How would they get on in this setting? Or we can try just various things like multi. So instead of me waffling, these are the ones we're going to try. We're going to try like a linear model and then a two-layer perceptron, and we're going to encode everything. So the input representations will have to be different for these different models. So we're going to have this outer product here between all the different words and then their locations. So this is going to be a sort of high-dimensional vector we're going to get that will feed into the MLP. The ConvNet, we can think about having the 2D layout of the grid and a different sort of color plane for each of the different objects. That gives you a way to represent the fact you have different objects at different positions. If you have two objects in the same location, you're going to do bag of words. And then you have the information items have to be encoded separately, unfortunately, in this representation. And then the final one, which I guess we spent probably most effort on, was this memory network model that Sina worked on previously. So I think Jason Weston talked about this in his talk a couple of days ago. Okay, good. Okay, so I'm not going to go into exact details of this thing because I think hopefully he explained it to you guys. So at least with the memnet, this is rough at a high level conceptually how it's going to work. So the idea is we have our controller, which in the memnet is something like an RNN. That's going to, of course, access the memory. Now, the memory of the memory network is actually going to be the game environment state. So the RNN can kind of access any of the different sentences, 1 through 10, in the at each hop, as it were, of the memory network. And each hop is one of these cycles, and then, of course, that memory lookup will then update the state of the controller and so on. And then the output of the memory network, which is at the top of the RNN, there'll be a sort of softmax, so different actions it could take, move left, move right, that kind of thing. And then, it will get some reward signal back. Now, typically this is very sparse. Most of the time it will get 0 reward. And then that will sort of, we can use to essentially train in a reinforcement learning setting this memory network controller. Okay, so when Jason described it, the memory network was trained with sort of standard sort of supervision at the end of the memory network. In this case, which is I guess the first time people have tried reinforcement learning with this memory network model, it's only going to come through a sort of very sparse reward signal. And then one sort of detail is, if you played around with reinforcement learning, to sort of get it to work well, it's helpful to have some kind of baseline estimate of reward at a given state that you can sort of use to give you a sort of relative measure of how well, of how good a particular action might be. So we do actually have two heads to this controller, one that predicts an action, another one that predicts some, scalar baseline value. Yep. Okay.
I just wanted to clarify.
Yep.
You have a name memory for the description of the environment.
Mm-hmm.
So do this description can contain previous steps? So
no.
If you have memory, it's like that you have.
Yes. Sorry, that's actually a good point. Right. So the word memory here is misleading. It's
it's a state.
It's the state. So effectively, these are Markovian games. Okay, that is that if you observe the state in the memory, that tells you all the information you need. Now, the one game that I described, which actually isn't quite like that, is one where you have to visit a whole bunch of goals, right? Because in some sense, you have to remember, I've already visited goal 1. Now I should move to goal 4 or something. And to do that, we actually have a little item I didn't describe called a breadcrumb. So it walks along, and the agent is allowed to drop a little crumb of bread at a given location, so that it can. Gives it a mechanism for remembering it's already visited location 1. But then, of course, when it moves away, it can. If it's purely Markovian, it doesn't have any way of remembering it's been there, but it can see the breadcrumb. It says, "Oh, there's a breadcrumb on goal 1. I've already been there. I should move to the next one." Okay, so effectively, this thing is it's not storing. The memory is not the previous actions or states of the environment. It's just the current state, but it then can do sort of random access into it. But this is an interesting point. We're actually playing around with sort of having the model, have a limited viewing window. So when it walks up, it goes, oh, here's a block. And then when it walks away, of course, it won't be able to see the block in the memory. But if you've got a sort of episodic memory type thing, then then it's more like what we think of as an actual memory. You'll be able to sort of remember that there was a block, in fact, over this particular location. Okay, now, so to train this thing, we're just going to use reinforcement. Oh, sorry, I'm sorry.
So I'm going to talk about the reinforcement algorithm that you used over memory network.
Oh, yeah, right. So yes, this is this slide. Yep. So essentially, it's pretty much standard policy gradient. Okay, so just ignore the right-hand part for a second. So the idea is that essentially, at the end of a game, you're going to get some reward. And we can use that then to update the parameters of the model. So that's going to be in the memory network, it'll be the parameters of the controller. In the other guys, it's going to be the weights in the convnet or the MLP parameters. And the way to think about this is the output of your model. So it's going to give you a sort of a softmax over actions, if you like. And theta is going to be the model parameters. So you're basically going to have some sort of gradient on that. And then you're going to have, this is going to be the reward signal you obtained at the end of each game. And then we do also have this baseline output. So that is, when you're at a current, there was some sort of baseline estimate as to what the reward would be. And you're going to subtract that off what the total reward is. Now, as I said, the model actually has 2 heads, right? So it's going to predict a baseline value as well. And so what's going to happen is that right, so this is the bit that updates that baseline. So you've got remember, it's got 2 heads, one that predicts the action, one that predicts the baseline, and this is the sort of part of the gradient that's going to come back down, the baseline prediction head. So you're going to train the model to predict a good baseline as well as predict a good action. That's the thing. So yeah, this is nothing particularly novel or anything like that. I guess it's somewhat novel applying it to the memory network, but other than that, it's sort of fairly much the same. Okay. Oh, yeah.
Explain more what is the baseline value?
So I guess it's okay. So I'm not a super big reinforcement guy, but the way I always think about these things is at some sort of intuitive level, it's rather like it's a reward relative to sort of what you might expect. So let's say you went to a casino or something like that, and you put $10 or something on some card game which had a 50% outcome. Yeah, exactly. So you would expect basically to get sort of $5 back, okay, if you played enough. But then if you somehow got $8 back, you'd be pretty happy, right? But if you got $3 back, you wouldn't be so happy. But the point is, if you might think $3 was, if you didn't have that baseline, you might think $3 was quite good. I mean, you might think you were actually doing quite well. But you have to realize in relation to what you might expect as sort of baseline value, actually it's not good. Yeah, so where are we? Okay, so now we're going to train, as I mentioned, on all tasks simultaneously, and we're very much going to use a curriculum. So the idea is we're going to adjust the difficulty of the game depending on how well it's doing. And we have various ways of things we can alter, the number of blocks, the grid size, and that sort of thing. And essentially, we're just going to dynamically tune those to sort of keep the agent always achieving the same sort of overall performance, right? So if it's getting 80% and it starts to improve to like 90, we're going to make the game harder, and then the performance will come down to 80, but it's now operating on a harder setting. And you can see, sure enough, that this is different models here. As we change the various parameters, we can alter the difficulty as measured by the sort of best reward we can achieve and things like that. Okay, so there's some details in the paper if you want to look at them, how we do this. I'm actually not going into too much detail. Basically, we train everything on a CPU, a single machine with many cores in a day or two, depending on the model. Okay, and then just to show you what actually things look like, so this is actually the memnet playing the multi-goals game. This is the state of the memory network at a given time. This is the attention vector over the different memories. So it's got 3 hops in the model, in the controller. So essentially, this tells you which of the memories it's looking at any given time. This map here is a sort of, this vector we're just going to remap into a 2D map grid, which is essentially telling you where is the model looking in the thing. So in this case, it's got stuck because it's impossible to. So this one is, in a second, it'll hopefully, yeah, okay. So in this one, you can see the network is attending to the target goal. So it's looking ahead at the goal and saying, that's where I want to be. And then we can look, this is the light key game. So here we go. So you can see most of the attention is actually on the goal thing. It's rather low contrast, but you can see there's some attention on the door and things like that. So the model sort of learned to attend to the kind of things that matter, ignore the other parts of the scenery that don't actually have any sort of impact on whether it can complete the task or not. So this is the push block one, I guess. So you can see, yeah, you can see that it's attending to things that it cares about. So as it's pushing the block, it's keeping an eye on the where it's supposed to push the block to as well. Okay, this science square. So as you can see, those 2 things. Okay, so this is effectively a sort of summary of the results. What I'm showing here is on this axis is reward. So what I didn't say too much about is the fact that for each game that we have a way of computing what the ground truth optimal solution would be. So anytime the engine completes a game, it achieves some reward, and we know what, if it had performed the optimal, had the optimal policy, what the reward would have been. And what we can look is a sort of ratio. So in other words, the way I've plotted it essentially is if it's at 1, it means the algorithm's figured out the optimal policy. Okay. Now the obvious thing is that actually most of the algorithms do not figure out the optimal policy. They do, however, solve the thing quite a lot of the time. But if you look at them visually, as you can see in some of these examples, they're not very efficient. They sort of bumble around a bit, go off in some random direction and come back and so on and so forth. And so that's one immediate observation. Sorry, what I'm plotting here is this is the results of a single model of each different type. So we trained, the 4 different model types with and without curriculum. That's the solid and sort of lighter colors for each one. And then what we selected the single best model over 10 runs based on the mean performance. Okay, so it's not like for each task we pick the best model. It was it's one model in, so say take the solid red one. This is the same model as this, is the same model as this, just competing on different games. Well, so the various sort of messages you can take from this, first of all, generally, having 2 layers seems to beat 1 layer fairly well. Probably the memory network ends up being the best model on average, although it's actually not that much better than the 2-layer model. The ConvNet does not that well. Okay, so ConvNet's have done very well for many image recognition tasks, but in this case, they don't seem to be so good at these more sort of abstract reasoning type problems. The curriculum definitely helps. You can see for each model, there's a little jump between when you add in the curriculum versus not having it. Okay, so just like children, you don't just start showing them relativity straight away when they're 5 years old. You have to build them up over time, and then they sort of maybe later on in life they might be able to understand it. It seems like the same is true of many of these machine learning algorithms. Okay. Now, one thing we did try actually. Yeah, sorry. Right. Yeah, the details are in the paper. I mean, yeah, roughly. So I think, okay, the memory network had 3 hops, and I think their RNN controller was, sort of like, they weren't huge models, maybe a couple of hundred hidden units at each layer of the RNN. And then in the ConvNet models, they were sort of, 3 or 4 layers or something like that. And the MLP was, again, like, 256 units or something like that. We did try different sizes. I don't think there was a vast difference in performance between them. So it wasn't, performance is somewhat, it's not like if we made the models bigger, it would necessarily nail the problem, I don't think. Now, one thing we also tried, actually, which is sort of, we haven't done such thorough experiments on, was I think but quite interesting and relevant for what you guys are doing, is one nice thing about having this text representation is you can give supervision in this nice form of asking questions to the agent. So as the agent, you can say, this is a way to give supervision without explicitly telling what action to take. So for example, you could ask the agent a question: what is a location, relative to you, 0, -2? So it's actually a wall. And then you could say, where's G5? So then it has to, look and explain that, right? So this is one way you can kind of, so you can, the point is, you know, once you decide on a certain type of question, you can automatically generate a ton of these question and answer pairs, which you can then sort of use as extra training data to help the thing. And this basically can let you learn the correspondence between sort of words that you're using and the objects in the game world. And you can add this as an info item, these Q&A pairs, and then you can see whether it can, so you can add the question as an info item, and then you can ask the model to actually predict the right answer for the question. So this is a sort of slightly, a way of using the sort of structure in our world to kind of inject supervision in some sort of fairly non-direct way. And this rather complicated plot tries to show that. So this is basically a bunch of different models. This was linear model with joint training, a combinatorial with joint training. These were 5 of the 10 games. This was a plot from earlier when we only had 5 tasks. What I've done here is we've stacked the rewards from each one of them. So smaller is better here, okay? You want to be small, but that would be, you're closer to the optimal reward. And on this side, I'm showing failure rates. So I didn't show that in the previous bar charts. I was just showing relative reward. And this is showing what fraction of the time do you fail the task. That is, you know, after some time limit, you just haven't figured it out. And you can see the contribution is sort of, you know, colored accordingly. Okay, so we can see here that in this case, conditional goals and multi-goals make, you know, it doesn't do very well relative to the optimal reward. Okay, now the ones that are relevant here. So most of the time, what we're doing is we're training this memnet jointly. So that's this one here. If you train it on a per task basis, it does help a bit. This is this row, but not too much. And then we did try adding in these questions to try and help the training. And it didn't really help in most cases, except for the red one, there's conditional goals. So in this case here, we were asking questions like, what color's the switch? Which goal should you go to? These sorts of things, okay, which are, you know, very closely related to the task itself. And it was able to, you know, with that extra kind of, you know, by being asked these questions, it was able to sort of figure out a better strategy of what to do. And therefore the reward, or the negative reward rather, you know, reduced a lot. The take-home message basically from all this, I suppose, is that you know, higher is better in these graphs, right? You want to go for 1. And for most of these tasks, except these ones down here, these standard models do not work very well. Okay, and that's sort of, in one sense, you know, frustrating, but in the other sense, I think it's encouraging because it shows us that maybe we need to think about being more creative and come up with new types of models to solve these types of reasoning problems. And so just to look a bit more detail, I mean, there's, for example, the conditional goals thing that involved this kind of conditional reasoning did not really work very well at all. And giving supervision didn't help either. So it was not like a failure of the reinforcement learning. In fact, actually, if you look at these bar charts, adding supervision in here doesn't really help that much, okay, over just doing reinforcement learning. So it's not the reinforcement learning that's killing you, it's the sort of, you just don't have the right models to basically do it. Yeah, so it can solve some tasks pretty well. And we'd also tried a fun thing where we tried giving it a new task it had never seen before, but would reuse the same elements in the environment. And it didn't seem to work very well at all. So that kind of failed. But that would be one thing that you would hope it might be able to do. Okay, anyway, so this tells us that you know, it's not like we're going to solve everything with a convnet here, okay? Or a memnet. We have to actually come up with new types of model. And one fun thing we tried to do was actually use this environment, this MazeBase, to try and attack problems in StarCraft. Okay, so this is Gabriel Senev. He's a postdoc at Facebook, and he's very interested in getting bots to play StarCraft really well. And what we used, in fact, was MazeBase to help us build a bot that we could then run in StarCraft. Okay, and obviously it wasn't the full StarCraft. It's not like it's, you know, building bases and controlling all the units. We had a little mini version of StarCraft which just had a very simple kind of combat, you know, scenario. And what we did was to basically kind of use MazeBase to very quickly approximate that scenario in MazeBase. And we could use the fact that we could construct a curriculum and all these things to train a model on in MazeBase that we could then actually evaluate in StarCraft and make run reasonably. Okay, and we did actually have a kind of cool thing, which I think we're hoping sourcing soon, which is basically a way of linking StarCraft to Torch. So at every step in StarCraft, you get a kind of dump of the game state that you can then pass into your machine learning algorithm and get some action. Okay, so it's a way to actually, you know, I mean, obviously people have been coming with bots for a long time for StarCraft, but most of them are based on rules. Whereas this thing, you could actually have a proper reinforcement learning loop in that. Okay, so the games we're going to play in StarCraft, just to very quickly show them to you, explain them to you. So I'm not a StarCraft person, by the way, so apologies if I'm mangling the terminology. There's a thing called kiting. Basically, the idea is here, you're going to pitch one unit which is quite fast but quite weak, this guy, which is what our agent's going to control, versus two slow-moving but kind of heavily armored units. And those ones can do a lot of damage, but they can only do it close by. All right. So how the question is, if you're nimble and fast, how do you beat, Goliath, as it were, right? You don't run up to Goliath and just, start attacking. You have to be smart, and the strategy is basically to run up, get within range, and then shoot at these guys, and then run away quickly while your weapon cools down, and then you can shoot again. So that's the sort of strategy the thing has to figure out. Obviously, it's got to learn it. We're not going to tell it that. And so just to illustrate, what I'm talking about here, so it's perhaps easier. So there's the fast-moving unit. It shot this guy, and it's going to run out of the way, and then it's going to come back into range again and shoot this guy, and then disappear quickly before this guy can do damage. All right. So this is called kiting, because you're kind of luring the enemy. I'm not quite sure. I mean, it's exactly why it's called kiting, but that's apparently what it's called in the StarCraft world. Okay, and there are some other sort of related versions. There's something called kiting hard, which is the same, but you have. So I guess that was kiting hard. We have two enemies. This one, the simplest version, you just have one enemy, and then there's also a sort of a different setup. We have 2 versus 2, where you have two. The enemy has 2 units of Terran Marines, and you have 2 units of Terran Marines, and you would like to be able to do the smart thing and be able to. Can you beat? I mean, in this case, the 2 units equal, so you've got to be smart about the strategy. What do you do? Okay. Well, the obvious thing, if you think about it, is that you should get both your guys to focus and fire on one of the enemy, right? Kill one of the enemy, and then it's a 2 versus 1 game. That's the obvious thing to do. But you want the reinforcement learning to figure that out. Now, what we did was to use MazeBase to very quickly prototype this kind of idea. So this is the same thing. Now we've got a little soldier. In this case, it's just one soldier, but we can easily, have multiple soldiers who will run after the agent. And we also can make it so we can have 2 agents, a blue agent too, and we can effectively, give the same kind of things, like you have health and you have a certain range, you can shoot and all this sort of stuff. And as a testament to how the MazeBase environment being very easy to kind of build new games in, even I did it. I actually coded this, and I'm pretty hopeless at coding these days. And I managed to do it in a few hours, even though I'm not a torch wizard or anything like that. And what we did was to then use, train the algorithms I was describing, the MemNet and the 2-layer multilayer perceptron with policy gradient in this environment. And this is just, you can see one of the trained models. It's doing sort of the right thing. So it's sort of, the flame is when it's shooting, and I think that thing is when the enemy shoots the agent or something like that. Okay. All right, and so what happened is, so we're going to compete against in-game AI, and we're going to measure the win rate, and the baseline here would be just to attack the weakest opponent. That's the sort of the dumbest strategy, just to sort of get a sanity check on how strong the in-game AI is. And so this is the 3 different games I mentioned. So you can see the attack weakest strategy works quite well on 2x2. It does not work very well on the other 2. It completely fails, in fact. Now, we had one version which we did manage to train the memory network on StarCraft, and this is sort of train and test in the same environment. For this particularly simple game, we were able to get the reinforcement learning to work in StarCraft, so you can see there it did actually do pretty well. And then the second one is really what I was, major point is that we're going to train on MazeBase and then test on StarCraft. And effectively what we had to do was just rescale the inputs in terms of how far you could shoot and things like that, and the damage that was done by shooting, and health and things like that. Just had to change those to match what was in the game, and then you can see it actually generalizes quite well, even though it was trained on the MazeBase environment. And of course, the key point, I guess, for more complicated scenarios in StarCraft, where you might not be able to, directly set up a curriculum or anything, you could use a curriculum in the MazeBase, right? So you could build up to sort of more complicated type things. Okay. And we are sort of, I guess the whole point is you can use this to sort of use MazeBase to tackle these more complicated problems. And we are thinking about more complicated scenarios as we go. Okay, so look, I guess I'll sort of stop there. Just to say, look, if you do want to play around with this, it's all open source. It's in Torch, for better or for worse. And, you're welcome to play with it. There's a sort of README file, which is, on the GitHub page, which explains how you use it. As I say, I do think it's fairly easy because I didn't write the thing myself. It was really Sina and Arthur Slam, the other one of the other main people on this. But I was able to use it myself fairly easily to write this whole combat game thing. Okay, so just to wrap up, I guess I've been talking about this sort of MazeBase project. It's a kind of sandbox for playing around with these AI-related games and reinforcement learning. We tried a whole bunch of these standard models, which have been very effective on other problems, on these sort of tasks involve, really what's very simple reasoning, but they didn't do very well. I mean, they're still a long way from being optimal, and we would like to develop new models, basically. So, for example, some learnable planning algorithm would be one that we discussed earlier. But I think, anyway, there's a lot of interesting kind of things we could do, perhaps in the space. So anyway, there's an archive link as well. So I'll stop here with this.
Some questions, please?
Sure. Yeah.
The first one, when you ask an agent how you modify architecture, additional actions.
Wait. I mean, the architecture of the agent of the model is fixed by us beforehand, right? So the agent has to learn all the games with the same.
Is able to answer.
Wait, I'm not sure. I mean, what's the question? You're asking the agent what question?
Question about environment.
Yep.
And how agent answer.
Or how does it answer? I think what happens is we, I see, yes, okay, I understand what you're asking. Okay, let's get back a second. So I think what happens is we use the, you're referring to this, right? How does it give the answer wall? Yeah, exactly. So I think it's an additional action. Yeah, exactly.
After that, agent able to resolve.
So that's right. So that's at training time, you have these questions, and at test time, you would just use the sort of outputs of the softmax that correspond to, move up, left, down, right. But you could imagine at test time also just asking the model a question, asking agent the question, where's the closest, which is the closest goal or something like that.
Second question is, why on the policy gradient?
That's a good question. I think Sinab tried the Q-learning thing too. I mean, I think policy gradients seem to work. Yeah, I mean, it wasn't really about coming up with new reinforcement learning algorithms, this thing, so.
Suitable for text?
Possibly, yeah. I mean, it's a little unclear to me, when Q-learning works best and when policy gradient works best and things like that. But,
could you please give more details about how do you compare different models when you have lots of tasks? For example, one idea you gave that you always evaluate the same model on all tasks, and that's how you. For example, we were working on Babi tasks, and we had a situation when the same model learns to pass one task in 3 epochs, for example, but for the other task it takes 50 epochs. And is it fair to say that our model solves both of them, or we should try to?
Yeah. Well, okay. So I think I would say, I suppose, is that humans are pretty versatile, right? I mean, one of the things about intelligence is you can sort of tackle a whole bunch of different problems with sort of the same underlying machinery. And I think that's sort of, we probably want to head to in these kinds of problems, right? You don't want to have sort of change hyperparameters or do different things for each problem individually, because then it's like, well, if someone gives you a new problem, what do you do, right? Whereas if you've got something that can solve, 50 different problems all in the same family, and someone gives you another problem roughly in that family, you would have some optimism it would work out reasonably well. Yeah. I mean, that's the motivation there. But I take your point, right? I mean, there are definitely cases where, one problem sort of, it's very difficult to get the model to solve both things because they require the model to behave very differently in perhaps similar settings or something like that.
How do you report the results?
Oh, right. Well, I mean, we did in.
For example, do these results come out of the same number of epochs or same?
Oh, I see. In terms of logistically, so I think that's right. So I think we just when we're training, we're mixing up in each. It's seeing many different games at the same time, right? So at a given time, every time. So one parameter update might come from. It's like in a batch of data, like in. Your one batch would be, a game that's a light goals, another one that's conditional goals, another one that's exclusion, and so on.
Okay,
So
they
it's,
can be
it's,
the same
they're all sort of mixed together, as it were, and therefore we just run a certain number of epochs.
Okay.
And it's true. I mean, you do see sometimes it takes a long time, and there's definitely, as I guess many of you also realize, like with these reinforcement learning algorithms, it's quite stochastic, right? Sometimes the models just don't really pick up what's going on, and other times you get a model that's like the genius model, you know, that kind of figures out what's going on and does much better in terms of overall reward than the other ones. So we do have there's a giant table actually that I didn't really show because it's a bit overwhelming, but we do actually sort of try to get a handle on this and showing the mean and the variance and things like that of the different runs. That shows the variation across the 10 runs and things like that. But yeah.
My question is about the way of interaction between agent and environment.
Mm-hmm.
You say it's the text. Do you suppose some structure of this text, or agents should learn from knowledge shared?
Yeah, it's the latter. That's right. So we're not. It doesn't know that, you know, it doesn't have any semantic understanding of what water is or what a block is, right? It has to learn through just experience.
Do you have a dictionary or it's chart-based? So what is the?
Oh, it's, you know, it's a dictionary. So the token water is sort of given, but and it's consistent across the different games, right? So that but it doesn't. It has to understand, learn for itself what that token does. It works. So you could replace these with arbitrary words, and it wouldn't make any difference to. But they must be consistent. It must be, you know, the same word means the same physical object in the different games.
Word basis or chart basis?
It's word basis. Yeah.
Okay.
Yeah.
Can we have two agents? One for control environment,
Mhm.
and two as a usual agent. It's like adversarial technique,
Yeah.
and maybe it's much interested.
Yeah. So I think that's a definitely very interesting direction. I mean, we're thinking about this too, right? I mean, at Facebook, you always have, you know, two people chatting with each other. They could be two agents. So this is something that we're totally thinking about. Yeah. I mean, it's on the to-do list, but, you know, we haven't quite got to it. So.
Do you have some research in this area? Or
No, I don't personally, but I mean, there's a whole little world of, you know, reinforcement learning, and where you have sort of multi-agent things going on. And I don't know much about the literature, but I think, you know, I'm somewhat optimistic that we could do fun things with all the deep learning stuff in that space that we haven't tried before. So.
I was just thinking about the perspective of this research, and you're just wondering what was the goal of this research in the first place? Were you trying to develop an algorithm that would become more transferable from one
Mm-hmm.
task to another, compared to convolutional neural networks on pixels? Is that?
Okay, right. So I guess what I've spoken about isn't really about developing a new algorithm per se. It's more about sort of one level of abstraction up. It's like, well, an environment where we might be able to develop better algorithms. And so the first stage, of course, in any new thing is you want to just understand how well your existing algorithms work. And that's really what I've been presenting. And so the hope will be that, as you can see, the algorithms all have some quite major shortfall and are able to solve these very simple things like, you know, if-then reasoning. And so maybe we, you know, the next stage is to try and think up ways to address that and to make sure the algorithms come up with new algorithms that can do it. So I mean, there's a sort of two levels of objective, I suppose. One will be to sort of highlight the deficiencies of existing models and maybe then use this environment for developing new models that could solve these kind of algorithmic type games. And then the sort of even higher level motivation will be, well, it's nice just to have an environment where we can play around very easily with different game environments. And so we can encode, for example, the combat games are different to the abstract reasoning games, and that we want an environment where we can easily prototype the different games and try different models in different settings and stuff. So it's a sort of one level it's a game environment, another level it's like, let's use that game environment to try and explore simple algorithmic reasoning. I'm sorry, I'm waffling a bit.
I want to add to this answer, if you can allow me.
Oh, sure.
I have a lot of knowledge about artificial style research, so there are also a lot of different simple games and stuff like that. And I see that the most like innovative feature of this problem, of this setting, of this project, is that there is description of the task in language. So and it is embedded in the description of the board. So usually you have like a world and you have fixed goal. Here you can just provide description of the goal to the agent, and the agent should solve this goal. So and you can give different goals, like different problems to the agent. And this is very flexible. So you can easily extend the environment and provide more goals, more different problems. So you can fine-tune your complexity of your problem very finely. And I think that it's great advancement.
Okay, this follow-up question, right? Is have you compared these algorithms with more like standard ones like DQN, for example, that is, I'm pretty sure can solve this problem?
So, well, I mean, in some sense, the deep Q learning, I mean, that's changing out the policy gradient for Q learning. But then the model itself underneath it is actually very similar to the ones that we have here, right? So, I mean,
I just thought that when you compare it to convolutional neural networks, you would use the words for training convolutional neural networks, and I'm talking about using pixels. You know?
That's true. That's true. Yeah, we could do that. It's true. I mean, it makes it a little bit tricky to. Yeah, I mean, it's true. I mean, you could do it. Yeah, I mean, it would make an interesting baseline and things like that. But I think, once you get, if you assume the first few layers of the network are just interpreting the representation from pixels into kind of, more abstract things, I mean, there's still the same basic machinery that's got to do the kind of reasoning behind solving the task in both the deep Q thing and the thing here, right? So it's not, you're changing the input representation and you're changing the reinforcement learning algorithm, but you've still got the same machinery that's got to kind of unravel the problem. So. Yeah. So actually, I mean, I'm not totally convinced the thing will be able to solve it. I mean, it's true that I can't say without with any confidence until we try it. So.
How you can explain if you go to the slide with this results for the different this one. So how you explain that usually the linear to layer is just bigger or the same as so what is your interpretation?
Yeah, okay.
They only say these multi-goals, yes.
Yeah, it seems to do better in some of them. But this is the thing where it's hard to sort of overfit a particular task, right? If you have the model has to do all these different tasks. So first of all, sorry, this linear two-layer is labeled wrong. It should be multi-layer perceptron. I mean, if you have two linear layers, it doesn't do anything, right? So you get my point. Yeah. So I think it's in some sense it's important to do your baselines very honestly, right? And you do see that sometimes actually quite simple things don't work that much worse than your fancy model.
And
right?
actually, you see no difference, almost no difference between curriculum and non-curriculum.
On some of the games, I would agree. Yeah.
Yes,
yeah. One thing I'm not showing here is, I guess, the failure rates. So the failure, I mean, the two sort of different ways. The problem is you can still succeed the task by just randomly walking around, right? It'll just take a long time. So it's a bit misleading, the failure rate thing to look at, but I don't know if you see it here.
But actually here they are correlated. So
yeah, they're pretty correlated. Yeah, reasonably correlated. Yeah.
So what is the set of problems which?
Well, okay. I mean, there are some ones here. I mean, some of these do show reasonable jumps between, using the curriculum or not. I mean, and it depends on the model too, right? So you can see that for ConvNet, which tends to struggle,
yes.
The curriculum really seems to help it, and so on.
Also for the MemNet too.
Yeah, and the MemNet seems to help too. I mean, I think a lot of people in different settings are finding that curriculums are very useful for training. I mean, in other papers, Wojciech spoke about some of the stuff we did on learning these abstract algorithms like addition and stuff like that, and that was the curriculum there was very important. And in general, it seems to help a lot of these things, that it's just too hard to kind of, figure out some complicated strategy or algorithm from scratch without, easy examples to get going.
But it's puzzling why this algorithm is memoryless. So it's just.
Well, I mean, yeah, that's right.
This
that's
one
right.
with the memory and why we.
I think.
So if it is just a pure Markovian, it's the case. So you don't need memory.
I think that's right. I mean, the way to think about this is it's a sort of slightly fancy version of an RNN or something like that would be one way of thinking. And in the way it's used currently, that's the way to think about it. I mean, there's not so much. Yeah, I mean, the RNN, obviously, it has some advantages over an RNN in the sense that the RNN imposes a sequence on things, whereas here it's a sort of an orderless collection of objects in the game world, and you can attend to any one of them out of order and stuff like that. So it does have that advantage, but admittedly, there's not so many objects in the game world that an RNN itself couldn't just keep them all sort of in its latent state. I think. I mean, which is true. Maybe should have tried in just plain old RNN. Actually, interesting to see what happens. Yeah.
Thank you so much. It's a strange question. How would you compare this environment to the neural Turing machine?
Right.
In the sense that, for example, the neural Turing machine have make a copy task, and it's basically the same. You can make a clear correspondence here, and you can use reinforcement learning.
Yeah, that's right. Yeah, you can. No, I think that's right. It was actually a somewhat conscious effort to try and attack the same kinds of problem from just a different angle. So one where you actually ground the problems in some sort of objects, and then you can see that we can train joint because we can reuse those objects in different ways in different tasks. We get this sort of transfer learning kind of effect going on a little bit. Multitask learning, what I meant to say. Whereas, so actually, I think it's actually in principle not that different to what things like neural training machine are trying to do, except that it's grounded in kind of objects in a maze rather than being abstract. Yeah.
That's one point, because it seems that if we just extract all the natural language processing from this environment.
Right. But I think, the language is useful, right? In the sense that you can imagine. I mean, it lets you do things like, for example, interact with it. I mean, you could ask the agent questions, and it will be able to give you answers in some human interpretable way. And then it does also. Language is quite powerful in the sense it lets you sort of alter the task by just changing the text that you give it, for example, which is what Mikhail was pointing out, and stuff like that.
The question is what is the main problem we're trying to solve with the multitask?
Well, no, there isn't really NLP precisely here, right? Because there's no sort of grammatical structure to the things, right? It's just tokens. But what am I looking for? Sorry, there's a certain where am I? Hold on, there was a sorry, just want to get back a second. So I mean, the neural Turing machine. I mean, they tackle these different sort of problems like copying and so on. I mean, you could. I think these types of reasoning are in the same sort of family as the ones that people tackle in NTM for sure. So they're just different. But it's, if you have objects, you can't manipulate the environment that you're in. There is no environment in some sense in an NTM, right? I mean, you're just given a number and you ask to sort of copy it backwards, right? Whereas in this one, you do have the option of sort of altering the environment you're in as well. So that's something that. Sorry.
But it's easier to do this kind of.
But it's not an explicit external thing. And you can imagine, if you want to play two agents against one another or something like that, I mean, it's helpful to have them both in a common, environment, right? Where, one agent pushes the block that way, and then that's got to changes things for the other agent. No, I mean, in principle, I think that the things we're trying to, I mean, if you think about it from a high level, what everyone's thinking about, we have quite good perception now with, conv nets for vision and you can apply them also to speech understanding and stuff like that, and even NLP as well. And so everyone's thinking like, well, what goes on top of these perceptual modules, right? It's some kind of reasoning ability, and this is some attempt to try and simplify things enough on the reasoning side that we can maybe play around with different deep architectures and figure out what works and what doesn't.
So actually, I can program an assembler.
Yes, of course. So this is basically a good way to obtain an intuition about how
something like that. Yeah, something like this. I mean, I think the thing is, I mean, the NTM is a very cool paper, but it's quite unclear, sort of, you know, what do you do next? I mean, how do you, or what's really going on, in fact, right? Whereas if you sort of wind back a few steps and take something a little bit simpler, and if you have the convenience of grounding it in simple language and stuff like that, then it's maybe easier to kind of really understand what the heck's going on and stuff like that. So.
You were talking about modeling some non-Markovian processes, and there's an interesting problem which can be formulated as when we should stop generating a pattern, because we cannot always rely on getting a reward in some kind of situations where we, well, like gambit in chess or something like that. So what would be a good architecture to predict patterns with their end? So to predict not only a pattern, but a moment when to finish.
Okay, so I'm not sure I totally understand the question, but I'm...
Yes. What is, to understand the question clearly, why we need, what is the case when we have to have a pattern with the end?
When we have some complex task, for example, reach the goal 1, then goal 2, then goal 3, and when we reach goal 1, we get some reward, but the pattern doesn't end.
Oh, I see. So you want to sort of, okay, all right. So, right. I mean, to the extent that sort of making a predictive model of your world is difficult, it certainly does make sense, I would agree, to break that, predict that model into sort of bite-sized chunks, right? You know, you would want to, yes.
That would mean that
it's tricky though, because in some sense you end up with a sort of greedy policy, right? Because you would say, okay, well, I'm just going to go for the nearest reward. You know, I'll run my predictive model forward, and I can see, oh, you know, 5 steps forward, I can get a juicy reward over there. So, you know, I'm going to go that direction. But if I ran my predictive model a bit longer, and if it was accurate enough, then I would see that, oh, actually, you know, there was a much better strategy just to do something else and ignore this one within five steps away. So there's I think it comes down to, like, you know, how good your predictive model of the future is, right? So in these little game environments, yeah, you can make things that are really good, but you know, in more complicated problems, it's harder to sort of roll forward that far into the future, right? I mean, yeah, and still hope that you have good accuracy. I mean, if you had some sort of estimate as to your uncertainty on your prediction, that would give you a natural way to provide some kind of limit, right? If your uncertainty just blew up at some point, you'd be like, well, you know, I have no idea what happens after tomorrow morning or something, you know. You know, so I would stop there. Yeah. I mean, I think it comes down basically to how complicated your world is and how good your predictive models are, which will determine how far you can safely kind of roll forward. But in terms of automatically figuring out when you should give up and, you know, a certain depth to that modeling, I mean, yeah, unless you have some internal way of measuring uncertainty reliably, I don't know how you would do it.
It actually depends on the environment where you are situated, because you should have some like most common length of the process or something like this. Because if you have no queues, what is the lifetime of any pattern? So you cannot just predict it.
Yeah. It's also, I mean, if you're in a deterministic thing like chess or something like that, you know, everything is completely deterministic. But any real world thing, you know, I mean, it's not, right? I mean, if I you know, if I have a little predictive model of like throwing a tennis ball against the wall or something, you know, I can predict it fairly reasonably what will happen after the first bounce. But then it's going to get complicated, right? Because, you know, it's going to hit some other object, and depending on where it hits that, it's going to go for some direction and things like this. So there's an inherent sort of uncertainty, I would say, in many environments, and that obviously that is going to limit. That's going to, you know, that certainty is going to explode essentially over time, as you, I think. So that would provide a natural limit.
So the idea is just to augment the generative model with some predictive model that estimates.
So that's one thing we're thinking about, for example, in this environment. Yeah, I mean, in the game environments, it's going to be pretty effective because things, but I mean, at least in these environments, are deterministic. You could easily imagine, though, putting in some kind of stochasticity into the environment, and that would make it harder to model and stuff like that. But yeah, but the people, you know, there's some interesting, you know, papers coming out on people doing this with various deep models, trying to sort of predict what will happen and stuff.
Thank you. More questions? Is the way to make these models, these games, not deterministic?
Oh, well, right. I mean, you control the environment, right? So you can do what you want. You can just.
Oh. I mean, in one game, for example, when your one game is.
Yeah, I mean, absolutely. I mean, so if you you can imagine a whole bunch of these games like. Yeah, that sort of thing, or like, you know, you could even make it so that you know, you have deterministic state transitions. So like, you know, you want to move left, but you know, you have gusts of wind that blow you, you know, so maybe you move down instead of left or something like that, right? Yeah, or something like this. So there's a bunch of, I mean, it's up to you to do it. But of course, you know, reinforcement learning deals with this, right? I mean, many of the standard algorithms assume a, you know, stochastic state transitions. So.
I have a question about this additional supervision. You added your questions, and I was wondering whether have you tried or considered giving an agent the option to ask the questions, like probably extending the action space. Yeah,
that's an interesting one, right? Because you can imagine it gets a bit stuck, and then it would ask a question. You could, yeah, that's actually fun. No, we haven't, but you could, yeah, it would be. It would be quite interesting to do. Yeah. I mean, this is just with reference to one of the other points over here. And this is one of the benefits of actually using text as the mechanism, because then, of course, if it wasn't, if you didn't ground it in language, in English or something, you know, ask you wouldn't be able to, you know, you wouldn't be able to ask you in any way that you could interpret a question, you know, a question. So. Yeah, it's a great point, actually. I mean, it would be interesting to see how that works. And of course, you'd have to make sure every time you asked a question, you gave it a negative reward, because otherwise it would just say, which way should I go next? And just keep doing that, right? So, yeah.
I'm curious, you know, it is very important when we develop robots for real things. It is important to simulate their behavior. And is it possible to map the real thing into your environment? Is it possible that your environment is expressive enough? And second, is it possible to do it automatically? I may give an example. Let's say if we produce a robot vacuum cleaner for this room,
okay.
And if let's say make a photo, and then we can automatically perhaps create a game. So that
I see. Right. I mean, I have to confess, you know, as you can tell, it's a very abstract little toy environment, right? I mean, you know, I mean, in principle, I don't see why you couldn't. Yeah. I mean, you know, if you know, had a convolutional network or something that you think would do a good job of just taking the photograph and figuring out, you know, which bits were traversable and that sort of thing, you could map into that. I mean, I have to confess, it wasn't, this thing, you know, frankly, wasn't designed for solving, you know, real world problems. It was more this sort of sandbox for playing around with different types of deep model and stuff like that. So, I mean, I guess you could use it for that. Yes. I mean, the truth is, it's really only, you know, a few thousand lines at most of torch code. So it's not a very complicated environment. And I'm sure you could add in stuff to tackle a real world problem. But yeah, I mean, in some sense, you might just do better just to play around with, you know, trying out, you know, adjustments to existing algorithms, just, you know, focusing on your particular problem, right? I mean, this thing was designed to sort of test things at a little bit more abstract kind of level.
It's very important, right? Because if you create some robot and you would like to talk to this robot, the robot can talk back to you. This is a great environment.
Yeah.
We will wait in 10 minutes from you.
Yeah.
And every room is different.
Well, it sounds an interesting application, but I do think this is a little bit of a kind of, isn't really intended to solve a real world practical problem. It's just to help you develop and think about new algorithms, I suppose. So.
And how you can imagine the future application of this research in some Facebook products? I mean, not now, not in the future, but just like in 10 years or.
I mean, well, what we would hope is that we would see that we would try out a whole bunch of different ideas in performing reasoning in deep models, and maybe one of them would work quite well on these sort of toy problems that we see here, and then maybe we would then try it on slightly harder real world problems. There's this whole I don't know if Jason mentioned it, but there's this Facebook Messenger product where you can in Messenger sort of ask questions like where's the nearest cinema that is showing, I don't know, a certain movie, and then you could say, well, can you book me tickets for it and things like this. And at the moment it's the responses are coming from a human operator typing, but we have but it's a great way to gather training data of these sort of kind of questions and answers and exchanges between a person and a digital assistant and an assistant, and then we have models that are trying to predict what the human operator would say, and you can imagine to be able to give good answers to the questions, you actually have to do some kind of somewhat complicated reasoning, and that you can, at the moment, of course, the responses aren't very effective from the machine, but we want to improve that.
But I just had an idea about this announcement of Zuckerberg that this year he will work on automation of his home.
Yeah.
So I decided that you should take, you have Maze project, and so you should say that this is house of the Zuckerberg. And if you can just type in what you want and then understand and move stuff around the house and stuff like so. You should sell this idea.
Okay. Well, it's a bit scary, I have to confess, because obviously, he kind of wants things to work, and So on one side, it's very exciting that he wants to do this. This is his goal. And on the other side, it's like some of us may have to spend some time helping him. But I think he did pick a few problems that are solvable. So I think, but anyway,
this is a nice model.
I mean, it's true that
so you can say just turn on switch in this room or something. Turn on.
Yeah. Well, if it's true, if he wanted to create, if he wanted to create a smart agent that would help him with that, so I mean, yes, you could maybe think about doing that. But
any questions? No.
Okay.
So thank you for a great lecture.
Thank you.